Quantum computing is reshaping the future of technology by offering unprecedented processing power beyond classical traditional computers. These machines, like quantum computers, leverage the principles of quantum mechanics to perform complex problems at exponentially faster rate than traditional classical computers. Quantum computing impacts a wide range of fields such as technology, finance, medicine, to name a few. Now let's try to understand what actually quantum computer is in reality. So quantum computers are analogs of the classical traditional computers. Unlike classical computers that operate on the classical bit, quantum computers operate on qubits or quantum bits 0, 1 and simultaneous superposition of 0 and 1 states. Quantum computers exploit basically three principles, that are quantum superposition, quantum interference and quantum entanglement. Let's talk about quantum superposition a little bit. Quantum superposition principles yields the superposition states of 0 and 1 state. Qubits are the fundamental comprising elements of quantum computers. Let's try to understand the growth of quantum computing over the years. Quantum computing has been at the center of technological revolution over the years, particularly in the last decade and this decade. Let's try to understand the timelines of quantum computing growth over the years. Back in 1994, Peter Shor gave us algorithm that's known as Shor's algorithm that basically says the quantum computers can break the classical encryption. In 2019, Google announced that it achieved the quantum supremacy, where they could achieve accurate outcome of a complex real life problem that would take around 10,000 years to solve in a supercomputer available in the world, but ultimately it took only 200 seconds to complete in the quantum computers. In 2023, IBM introduced Condor, that's setup of 1121 qubits to push the building of quantum processors. In 2025 and beyond, we can expect huge development of quantum error correction, quantum network, that's quantum internet, quantum communication and commercial quantum computing development. Let's point out some applications of quantum computing in today's age. Quantum computing is very much applicable in the fields of cryptography and cyber security these days. Quantum computers can break the classical encryption techniques RSA, AES, basically shifting to post-quantum encryption era. It also enables unhackable quantum encryption by using quantum key distribution QKD. In drug discovery also, quantum computing is very much applicable in protein folding simulations and drug designing at exponentially faster speed at the quantum level. That basically enables to build complex yet accurate drugs at much faster rate than classical traditional computers. Another field where quantum computing is hugely applicable is the finance sector. Quantum computers can enable the portfolio optimization in finance. It helps in stock markets also. Quantum computing is the next biggest revolution in today's world. Not only technology, but the fields like medicine, finance, etc. have so much wide range of scopes for quantum computing. And quantum computers can perform those tasks at much faster rates than classical traditional computers. Quantum computing has so much challenges also, apart from the conveniences or advantages. Few challenges of quantum computing that are required to be mentioned are quantum decoherence, high costs, scalability, etc. Now, the qubits are fragile. These need to be stored in extremely low temperature. Now, scalability. Quantum computers need high number of qubits for extremely accurate results, which is a daunting task as of now. Although quantum computers can perform more accurate results than classical computers and can perform at exponentially faster rate than classical traditional computers, it yields errors also in the outcomes. So for that, quantum error correction is required. And high costs. Quantum computers are very much expensive. For building quantum computers, it requires millions and billions of dollars. So it's very expensive. Quantum computers perform via construction of quantum circuits and measurement of the qubits at the end of the circuit. Let's try to understand what actually quantum circuit is. Quantum circuit is basically a circuit that consists of qubits in the beginning and quantum logic gates in the middle of the circuit, and at the end measurement operation is there to end the circuit. What are quantum logic gates? Quantum logic gates are basically unitary operations. These quantum logic gates are mathematically expressed as unitary matrices. Let's point out some examples of quantum logic gates that are widely or used in quantum circuits. Some quantum logic gates are Pauli X gate or sigma X, Pauli Y gate or sigma Y, Pauli Z gate or sigma Z, Hadamard gate, phase shift gate, control gates, identity gate, etc. A Pauli X gate basically is a bit flip gate that acts on quantum state 0 to convert it to quantum state 1 and vice versa. It basically maps 0 state to 1 state and 1 state to 0 state. Now, Pauli Y gate maps quantum state 0 to I quantum state 1 and quantum state 1 to negative I quantum state 0. And Pauli Z gate does not change the quantum state 0, but it acts on quantum state 1 to make it negative quantum state 1. That's basically the amplitude negative in this case. Identity gate basically is a identity matrix. Hadamard gate operates on quantum state 0 to convert it to 1 over root 2 summation of quantum state 0 and 1, and Hadamard gate maps quantum state 1 to 1 over root 2 quantum state 0 minus quantum state 1. These are some examples of quantum logic gates that are very much useful in constructing simple to complex quantum circuits during the performance of complex problems in quantum computation.